Thank you very much. Good afternoon, everybody. First of all, it's really my great pleasure to thank the organizers for bringing us here to this wonderful conference, and thank you in particular for giving me the opportunity to speak here. And also thank you to you all for sticking around so late. I'm going to present two types of work. The first is with a set of fantastic collaborators from Heidelberg first, Björn Friedrich, and then from Hamburg, postdocs Jeroen Monet and Max Wiesner, two outstanding postdocs in Hamburg. Max Wiesner, in fact, is starting his independent research group this January in Hamburg. And the second part of the talk will be with the wonderful Mario Rake from CERN, postdoc at CERN at the moment. So the overarching goal of the talk is a goal that we all share, namely we would like to find certain constraints on quantum gravity. So how do we go about? Well, clearly, since this is quantum gravity, we have to start with some idea based on certain assumptions, which of course include considerations of consistency of the theory. And clearly, the stronger the assumptions, the stronger the result and the outcome. The most successful example being string theory with very concrete assumptions about what happens in the UV and very strong predictions. The swampland program is the attempt to weaken some of the assumptions and see how far one can go without putting a particular type of UV theory in from the start. But then we would like to test these ideas, ideally, and in principle, the way to go would be to rule it out. This can be done either with the help of a theoretical laboratory. This could be in the context of mathematics or some framework that allows us to test these general ideas. And of course, another laboratory would be an actual laboratory corresponding either to the universe in the sense of cosmological observations that might give us clues about the underlying assumptions of our ideas, or an actual experiment. And clearly, the second type of observations and experiments are very difficult in the context of quantum gravity, simply because the energy scale of quantum gravity is very much higher than the scales that are currently achievable directly in experiments. So in this talk, I'd like to exemplify this for two sets of ideas and two different types of potential tests. The first idea comes from the realm of the swampland program, in particular the distance conjecture and the emergent string conjecture. I will say and review more what this means. And the laboratory in this case is of the first type. It's a theoretical laboratory. It's geometry, more precisely geometry of stable degenerations, which I'm going to explain. And the outcome is that this laboratory of stable degeneration geometries provides evidence that the emergent string conjecture is indeed realized, in particular in the context of type 2B string theory on Calabi-Yau threefolds at infinite distance in complex structure. I will explain what these words mean. The second type of ideas is more general even. It's about the ideas that axions are a generic outcome, maybe a universal outcome of string theory. And the laboratory to test this would be axion experiments or observations of axions in cosmology. And the statement I'd like to defend is the following. If we find an axion-like particle in either of these two contexts, whose coupling to charge mass ratio is larger, significantly larger than the coupling to charge, than the coupling to mass ratio of the QCD axion, then this rules out the perturbative heterotic string. That's the claim. So these two ideas and statements I will discuss in the two parts of the talk, and I start on this side. This will be maybe 70% of the talk, and then at the end I switch to idea number 2. Okay, so part 1. So since I'm the last to speak, I have the privilege of drawing upon the rich amount of material that was already discussed beautifully at this conference. In particular, in the talks of Gary, Fernando, and Hichol, we learned a lot about the swampland program. And we all know now, if we didn't know it before, that this idea of the swampland program is to identify universal properties of quantum gravity without putting in a UV theory to start with. And among one of the ideas that has been discussed in this context is the insight that in gravity, a property is that of UV-IR mixing, namely that even in the infrared, one is able to kind of trace back effects from the high energy completion of the theory. And one aspect of this, more precisely, is the appearance of light states, which results from the details of the UV completion in quantum gravity. Nonetheless, even though this is something that appears at high energy scales, there are light states that we can observe in the infrared, at least in asymptotic regions of the moduli space. And that statement is precisely the statement of the swamped distance conjecture that was reviewed in detail, in particular in Fernando's talk. Light states from the UV completion quantum gravity show up in the infrared in asymptotic regions of moduli space. So if you have a theory with a moduli space of couplings, and if we go to regions in this moduli space that are asymptotically far away, in particular asymptotically weak coupling, then the claim is that states become light, which are really gravitational states. And the shocking thing is it's not just a handful of such states, but infinitely many states. A tower of states becomes light as we move to infinite distances in the moduli space, exponentially in the distance in moduli space. That's the famous swamped distance conjecture. And it's a very important statement for the swamped program for various reasons. In particular, you could ask, why are we interested in what happens asymptotically in the moduli space? One answer is because these asymptotic regions are the regions of weak coupling. So you would think that the asymptotically weakly coupled regions are the ones where you understand physics best. But the statement of the swamped distance conjecture is that in gravity, this is not necessarily so, because new states from gravity come into the play and cannot be ignored. So if you have a field theory and you're happy with it and you go to infinite distance in your coupling space to zero coupling, beware, as soon as you couple it to gravity, you must take into account these states from the UV completion because they become light. That's the message of this claim. Again, parametrically recoupling regions and the difference between weak and strong coupling in these asymptotic regions was discussed in detail by Fernando. And in fact, also for cosmologists, this is an interesting statement because these regions of asymptotic coupling are also candidate regions of interest for late-time cosmology in the context of the cosmological constant, the so-called dark dimension scenario, which some of you may have heard about, goes back to these ideas. And once again, the shocking thing is that at such asymptotic coupling regions, the cutoff of the theory is not really the Planck scale where you would expect it, but the cutoff of this theory goes down. It goes down in particular sometimes below the naive cutoff from quantum field theory. This is because these light states change the running of the couplings and must be taken into account. So that's the distance conjecture. What the distance conjecture does not yet tell you is what are these states and what is the value of this cutoff for the theory at infinitely, say, weak coupling. So we need more refinements, and a proposal for a refinement is the emergent string conjecture, and the context of that one is that it specifies the tower of states that becomes light, and the claim is these towers can either be Kaluza-Klein towers in some duality frame, or they can be excitations of a weakly coupled perturbative string. So you have a theory, you go to infinitely small coupling, and then the claim is either new dimensions open up, or a string becomes weakly coupled and relevant, even if the theory in the interior was not a string theory. So we are not assuming that the theory to start with is a string theory in the bulk, but the claim is that at least asymptotically, the theory becomes either a string theory or it becomes a higher dimensional theory. And in particular, if you make this assumption, or if you make this claim, then from this you can compute what the cutoff of the gravitational theory would be. In the string case, the cutoff would be the string scale, the scale of the string whose tension becomes small with respect to the original Planck scale. Or it could be, in the case of decompactification limits, the higher dimensional Planck scale. So this has a lot of predictive power for the swamped distance conjecture because it constrains you which type of limits are possible. And there have been a number of recent applications to classifying possible boundary behavior, including these works and others. Okay, so this is a strong claim. So it needs clearly evidence. And there are various types of evidence that one could think of. In particular, string theory is for us a laboratory in which we can try to test this statement. So we can now assume or consider the particular framework of string theory as a particular framework for quantum gravity and check whether the distance conjecture and also the emergent string conjecture hold in this context. And this has been done in great detail in the literature, mostly in limits in Kähler moduli space. So we go to infinite distance in the Kähler moduli, which control the sizes of the cycles of the compactification space. And it has been shown in all cases studied so far that the limits indeed are always one of the two types, either by some duality, a decompactification limit or a string limit. And this oftentimes, in fact, relies on the appearance of quantum corrections. So a lot of connection to also nice mathematical results in the description, in the geometric description of moduli spaces are made in this context. And the key idea here is that in these Kähler limits, what usually happens is that some object becomes light because it wraps a cycle that becomes small. And this then either becomes a KK tower or gives rise to some new critical string which sets the new duality frame. So in this talk, I'm going to continue the tests of the statement, again within string theory as our laboratory, but looking not at the Kähler moduli, but the complex structure moduli. So more precisely, I'm going to consider now string theory compactifications to 4 dimensions on a Calabi-Yau threefold. This is a theory of 4D n equal 2 supersymmetry, so 4D n equal 2 supergravity effective field theory. And then I'm going to consider the infinite distance limits in the complex structure moduli space of that theory. And I want to see, do states become light? And if so, can I always interpret them as either KK tower or as excitations of a string? And at first sight, it's not clear at all why this would be so. Because the complex structure moduli, what they do is they describe the shape of your space. So if you go to a limit where the complex structure moduli are taken to infinity, this means that the space becomes highly anisotropic. I somehow change the shape of this internal space in a very extreme way. And while it's maybe obvious from this picture that maybe some states become light, it's not at all clear why they would be KK states or why a string would be emerging. And it turns out that this is also a non-trivial question to tackle if the interpretation of states upholds. And in fact, there are 2 complementary ways of thinking about this problem. Historically, the first was in the algebraic context by considering what's known as the algebraic limiting mixed Hodge structure of those theories. We don't really need to know too many of the words. Of course, I will describe those that are relevant really for us. The idea is here to look at the periods of the Calabi-Yau, so the integral of the 3 form over the 3 cycles. Their expectation value essentially can be identified with the values of the moduli in complex structure moduli space, which I take to infinity. And by using this, this beautiful technology of algebraic limiting mixed Hodge structures, these authors, starting with this paper by Grimpalt, Valenzuela, and then many others, were able to extract a lot of information about the effective field theory and the supergravity in the limit. So in particular, we can see how the couplings behave asymptotically in this limit. And one can also deduce what candidate states could become light in the limit, namely the 3 branes wrapping 3 cycles which become small would give rise to certain towers of particles. And if these states are there, their masses can be determined from this effective field theory and supergravity approach. And one could check that, for example, this exponential behavior of the mass in the distance in moduli space would indeed hold. However, this purely algebraic approach only gives you candidates for light states. It doesn't show that these states are actually there, in particular, not that towers of these states are there. And it also doesn't give you an interpretation of the states. And in order to add these pieces of information, we have to look closer at the geometry as well. So this would give rise to something known as a geometric limiting mixed hot structure. In this way, we supplement this information by knowledge about the explicit nature of the 3 cycles that become small. And in particular for this one, this is needed in order to prove the existence of states of towers becoming light and to understand the nature of these states. So KK tower versus string excitation tower. For this, you need to know more than just the effective field theory. You really need the geometry. And this is, so to speak, where the UV input, in this case from string theory, really comes in. I spoke about UV-IR mixing. Indeed, the UV information is the one encoded in the geometry. And this a way of thinking geometrically about these complex structures was first done, in fact, in compactifications in F-theory with Sinju Li and also Alvarez Garcia and with Wolfgang Lerche. And then more recently, we looked at non-elliptically fibered Calabi-Yau threefolds in these works. And this is what I'm going to discuss today. So that's the one slide message at the highest level, so to speak, combining the insights from algebraic analysis, algebraic limiting mixed hot structure, and geometric limiting mixed hot structure allows us to eventually indeed find evidence for the emergent string conjecture in this laboratory of type 2b Calabi-Yau compactifications in complex structure moduli space. So that's what I'm going to now detail a bit more. Okay, let's get started. So we have to think of a good way of how to picture geometrically, and I should say I will start, even though this is not the chronological order, I will start with the geometry and then supplement it from this algebraic point of view to the extent that I need it. So geometrically, how do we think geometrically of a Calabi-Yau, say, at infinite distance in complex structure moduli space? The right way to think about this, or the useful way in this context, is in the language of semi-stable degenerations. What does this mean? It means that your Calabi-Yau threefold splits up into a union of various threefolds which intersect non-trivially. That's what a stable degeneration is. And the simplest way to picture this is to take not a Calabi-Yau threefold, but a Calabi-Yau onefold. This would be a torus. So at infinite distance in complex structure moduli space, what happens to the torus? It splits up, for example, into 2 components that look like this. Each of them would be a rational curve. They would be glued together, or they would intersect in 2 points. And we already see that in this case, in this way of picturing it, there's a small 1 cycle in this case, middle dimensional cycle S1. Namely, this is this S1 here, which pinches off and which is localized at the intersection of the 2 components. And all we need to do is generalize this picture now to higher dimensions. So rather than a Calabi-Yau onefold with an S1, we are going to look now at a Calabi-Yau threefold, not with an S3, but as it turns out, with some middle dimension manifold of real dimension 3. That shrinks. And shrinking means once wrapped by a corresponding D-brane will give me a particle. And that's the particle tower. So more precisely, the Calabi-Yau threefold at infinite distance. So suppose we have here our moduli space. This would be a 1-dimensional slice of the complex structure moduli space. Now I go to infinite distance, which I draw here in the origin. So what happens is that we have a family of Calabi-Yaus whose shape differs, as drawn here. And at infinite distance, which here is in the origin, this Calabi-Yau threefold degenerates. It splits up into a union of threefolds which intersect non-trivially. So the threefold at infinite distance becomes a union of threefolds, in principle arbitrarily many, and they can intersect. And this is in fact what you immediately see with the simplest type of Calabi-Yaus that you can think of. How do we think of Calabi-Yaus? We like to think of them, for example, as hypersurfaces in some space. This would be the simplest way of modeling them. Let's take such a hypersurface, for example. We have here now 2 moduli, U1 and U2. Tuning them will change the shape of this hypersurface. Let's go to infinite distance, take U2 to 0. This means that this term becomes infinity, so the hypersurface really splits up. Only this term becomes relevant. It splits up into the union of x1 to 0 and x2 to 0. These are the loci of 2 threefolds, v1 and v2, given by these equations. And that's precisely an example of such a splitting. So this is how we should think of infinite distance degeneration. Yes, please. Yes, I will come to this. So this is just the simplest example. In general, we can have several components. And indeed, yes. The Kähler interpretation. So this is complex structure. In the mirror, very good. So for this particular case, the mirror interpretation is that the Calabi-Yau has a K3 fibration. And in the limit, the base of the K3 goes to infinite volume, while the K3 fiber stays volume order 1. That is the mirror dual degeneration when a mirror dual exists. Yes? In the mirror dual, the light particle comes from an, first an M5 brain wrapping the K3 fiber. This gives you a string, heterotic string. And second, D2 brains wrapping curves in the fiber. Yes, but I light with respect to the Planck scale. Yes. Furthermore, there's another complication which I now didn't say. In type 2a, we also have to co-scale the string coupling GS to infinity on top of that because we want to move in vector multiple moduli space, and this gives you an extra suppression factor. So this is precisely the Kähler side that was discussed in detail, as I showed. I don't know, on the third slide. Good. So infinite distance, Calabi-Yau splits up into various components. They intersect. And now comes the message. The classification of possible limits amounts to classifying the ways how these components can intersect. That's all we need to know. Namely, these components, these are threefolds, they can now intersect now on a surface, on a complex surface. This would be codimension 1. Then the complex surfaces can intersect again. This would be codimension 2 over a curve. And the curves can intersect again over points. This would be codimension 3. And the way how this happens classifies or divides these possible infinite distance limits into 3 possible strata, 3 different strata called type 2, type 3, and type 4. In the type 2 case, the individual components intersect over complex surfaces, but the complex surfaces don't intersect further. This means that the codimension of the highest intersection locus is 1, namely the surface. This is codimension 1 in the threefold, and the surfaces don't intersect further, so the highest codimension that appears in this case is 1, d equals 1. Second possibility, the surfaces intersect over curves. The curves have codimension d equal 2 in the threefold. All the dimensions are complex dimensions here. So this would be d equal 2. This is the case where the surfaces intersect over curves. And then the third possibility, type 4, d equals 3, where the curves can also intersect over points. So for example, the large complex structure point that many of us know is an example of this type 4. And that's the geometric picture. That's almost all we need. In fact, there's one last piece of information, namely, the claim is, once we have the structure, from this we can also read off that certain real 3 cycles shrink in this real 6-fold or in this complex 3-fold in this Calabi-Yau. And these real 3 cycles are precisely the generalization of what I showed for the torus. On the torus, this was a 1-fold, complex 1-fold, and I said an S1 shrinks. Now, what happens, and I will discuss this in a bit more detail, is that a 3-cycle shrinks, a real 3-cycle shrinks, and this 3-cycle is given by a torus fibration over a curve. The torus has real dimension d, where d is 1, 2, or 3. So this would be an S1, a T2, or a T3, fibered over a curve of real dimension 3 minus d. So T1 over curve, and so on and so forth. Now these are real dimensions. And this gives you a 3-cycle whose volume shrinks. So again, this is the picture for the torus, T2. There we have a shrinking 1 cycle, and this is localized at the intersection of the 2 components. And now for the higher dimensional case, this is a generalization thereof, just that we need to take into account that the topology is more complicated. It's not just an S1, but it's a torus fibered over a curve of this real dimension 3 minus d localized at the intersection. That's the intuition. And what shrinks is the radius of this fiber, as we can see in this picture. And that's why small 3 cycles arise. Wrapping the 3 branes on them gives particles which become light, and these are the particles of the distance conjecture. Precisely. This small d is precisely the small d in d equal 1, 2, 3 of type 2, 3, and 4. I'm not sure how well known it is. So it's certainly our proposal. I haven't seen the statement written that clearly in the math literature, but that might just be that I haven't found the place. And but one can, in the paper, we argue for this based on the properties of the degeneration. So this classification of degeneration in the geometric case, this of course is known from the math literature, and it's yes. And our proposal is that the vanishing 3 cycles have this topological structure. Yes, I come to this. So more precisely, let's work it out. Let's first take the case type 2. What is type 2? Type 2 means Calabi-Yau 3 intersects into 3 folds, and these 3 folds intersect over a surface. For example, a K3 surface. Okay. So in this case, the 3 cycle that becomes small takes the following form. It's a 1 cycle fibered over a real 2 curve, a real curve. And this real curve lies on the intersection locus over which the components intersect. We will discuss this more in the type 2 case. But the important point to see is that the fiber is only 1-dimensional. Why? Because the intersection occurs in complex codimension 1. So this complex codimension, like in this picture, has a large and a small azimuthal direction, so to speak, which shrinks. And that's why an S1 fiber is localized at this point. And in fact, this point is now a surface, complex surface. It contains a real curve of real dimension 2. And fibering this over this curve gives a 3-fold in the real sense that vanishes. And in fact, one can now write the data of the curves over which we find such a fibration in this diagram. And this diagram shows that there are 2 plus b such types of curves. 1, 1, and b, where b is a parameter that distinguishes the type of the limit geometrically. We'll discuss this more. Next, type 3. Now this means that the surfaces of intersection intersect again over a curve. So we have 2 normal directions to that curve, 2 complex normal directions, each of which contains an S1. So we have 2 S1s that shrink. This is a torus, and this can be fibered now over 1 cycle on the curve of intersection. And as it turns out, there are precisely 2 such 1 cycles, because that curve of intersection essentially is a torus, or at least the relevant part for this construction. This is a 1 and a 1. 2 such 3 cycles that we construct as T2 fibrations over 1 cycles, 2 1 cycles in the curve of intersection, the relevant part of which is a torus. And then the simplest would be type 4. So the worst degeneration is the simplest, because now everything intersects over a point. Codimension 3, therefore. Complex codimension 3, so we have 3 1 cycles, S1, 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 gives a torus fibered over a point. So this is literally the analog of what we saw for the torus. And there's only 1 of them. More precisely, this structure is what constitutes a geometric limiting mixed hot structure, as described in these papers. I'm not going to discuss in too much detail what this is, but we have a review of the relevant parts also in our work, and you can ask me later. The important point, however, is if you see that that type of structure here, and you listened to or you read the papers of in the swampland community, you will immediately realize this diamond as something that was previously discussed in the algebraic context. This is the Deligne splitting for the 3 cohomology in the vicinity of an infinite distance limits from an algebraic point of view. And that's what's known as the algebraic limiting mixed hot structure. That's the statement that near a point of infinite distance, the middle cohomology, H3, splits into 7 graded spaces, G0, 1, 2, and so on, up to 3, 4, 5, 6. So these are spaces of 3 forms, but 3 forms are dual to 3 cycles. And in particular, the space called GR2 here is dual to precisely these types of 3 cycles. GR1 is dual to precisely those 3 cycles, and GR0 is dual to this 3 cycle. And what now the algebraic point of view gives for you is it computes for you the volume of these 3 cycles in a limit when we take S to infinity, where S is the complex structure modulus. So they don't phrase it in this way. What they phrase it in terms of the Hodge norm of elements in H3 as one approaches the infinite distance. But that is dual. That is the volume of the dual of the Poincare dual cycle. And the key result of this analysis is that these 3 forms of these different types, dual to corresponding 3 cycles, scale in the infinite distance parameter in precisely this way as 1 over S, 1 over S squared, and 1 over S3. And why is that? Well, look at how these were constructed, how the dual cycles were constructed. The one that goes, whose volume goes like 1 over S has one cycle in the fiber that shrinks. The one shrinking at rate 1 over S squared has 2 1 cycles in the fiber that shrink. And the volume going like 1 over S cubed is a torus, so 3 cycles in the fiber, which is the total space of the 3 cycle that shrinks. So apparently, geometrically, what happens is that in these 3 different types of limits, the fiber always shrinks at the same rate per 1 cycle, and this accounts for this peculiar vanishing behavior, which is the content of a theorem by Catani, Kaplan, and Schmidt in the algebraic case. Yes? Taking into account what? Good question. So yes, you would have to intersect that with H3 of Z, and this would then be those spaces, indeed. Yes, it takes this into account. Intersecting it with H3Z will give you the elements in, that would be Poincare dual to that. If they exist, you may have combinations, but these will then not be the ones shrinking at the fastest rate. If you're interested in the states shrinking at the fastest rate, you should always look only at those rows that shrink in the fastest. And in particular now in a type 2 limit, these 2 rows are absent, so we stop here. In a type 3 limit, it goes only up to here, and the last one is absent. So if you want to look at the cycles that become that shrink fastest, hence if you look at the D3 brane states that become light fastest, you have to look at only the lowest row. Good. So, and the claim is now, this was mathematics, 2 types of mathematics, geometry and algebra. The algebra gives you the scaling, the geometry gives you the interpretation and the topology of these cycles in these 3 types of limits. And if we now also include physics, then, and this is what I'm going to do in the remainder of this first part, one can show that these limits indeed classify as deconvectification limits from 4 to 5 dimensions, from 4 to 6 dimensions, or as weak coupling limits of a certain dual string theory, respectively. And that's precisely the claim of the emergent string conjecture. So now I'm going to exemplify this, beginning with the easiest case, type 4, then I go to type 3, and then to type 2. Okay, so let's start with type 4. Type 4, again, I want to show again, this would be the last case. This means that the components intersect in a complicated way over a point, and there is one torus that arises as a T3 fibered over that point. And all the tori, all the different points carry tori that are homologous to one another. There's only one of them, as is shown by this geometric limiting mixed structure. So we have one 3 cycle whose volume goes to 0 at the fastest rate, 1 over S cubed. Now, if I wrap a D3 brane on it, this gives me a particle that becomes light. And if I can wrap multiple times, in fact, infinitely many types, then I get a tower of particles. And the claim is we can do that. We can wrap multiple times. We get a tower, and not only do we get a tower, but this tower behaves like a Kaluza-Klein tower. Why is that? The reason is that the tower, that the cycle that shrinks is a 3 torus. A 3 torus allows multiple wrapping, infinitely many wrappings, and the wrapping number at each wrapping number, the number of BPS states is the same. So wrapping the D brain once gives me particles, wrapping it 100 times gives me particles, and they are counted by the same number, by the same BPS index. The BPS index is independent of the wrapping number. This is a property of the torus. And our analysis was necessary in order to establish that these 3 cycles have the topology of a torus. If it were an S3 that vanishes, we could wrap precisely once, and that would be it. So for the distance conjecture, we need infinitely many particles, a tower. So this topology of the torus is crucial. Furthermore, since all the wrapping numbers are the same, this is exactly the behavior of a Kaluza-Klein tower. If you think of a theory, say, going from 5 to 4 dimensions, you have the famous Kaluza-Klein tower of particles, and you see that at every Kaluza-Klein level, the degeneracy of particles is the same. That's a property of particles of the Fourier modes along a circle. And this is precisely represented by the fact here geometrically that the wrapping number of the torus, at each wrapping number, we have the same BPS degeneracy. So this establishes that not only do we have a torus, do we have a tower, but it behaves like a KK tower. So deconvectivication to 5 dimensions. Please. Where? In which case? Some twist. But this will not, okay, good. However, this is not realized here because the BPS states are only the untwisted ones. And I think, and this would also not be compatible with the preservation of supersymmetry. Yes, exactly. While here we don't. Yes? Yes, so the mirror of this would be the large scalar limit. So one has to be more, there's also a secondary, the secondary index of the singularity. And if this is highest, then the dual of this is the large scalar limit. So this is just the limit where everything becomes large. And we have to also scale GS in order to stay in the vector multiplet moduli space. And this tower then is dual to the tower of D0 branes, bound states of D0 branes. That was discussed a long time ago by Pillion. Good. So this is the physics. There's also an add-on for math now. Namely, if we, by this physics argument, we can now make a prediction for mathematics. Namely, we can argue that this number is independent of n is clear because it's a torus. But what is the value of this number? And we claim it's given by minus the Euler characteristic. And this follows from the physical interpretation. Namely, we have argued physically that these particles are a KK tower from 4 to 5 dimensions. So what this should give us is, in fact, the BPS index of 5-dimensional particles. So this BPS index in 5 dimensions is written in this way in terms of the SU2 right and SU2 left Lorentz symmetry in 5 dimensions. It's an index, so it comes with a minus sign, as is very well known. And computing this index is known to be given by this combination of 5-dimensional hyper and vector multiplets. These are easily related to the Betti numbers in 4 dimensions of the Calabi-Yau. So plugging this in gives you precisely minus the Euler characteristic. This is -1 because this is the number of vector multiplets, not of vectors, but of vector multiplets. So we have h to 1 many vectors, and this is one gravity photon, and the rest are the vector multiplets. And the gravity multiplet is inside this 4 here. That's why I subtracted here. And if we have a mirror dual to large scalar structure, then this result is known as precisely the statement that the number of D0 branes in this context is given by minus chi. of the dual, of chi of the dual, which is minus chi of this. But this argument did not use mirror symmetry. So it's true also for degenerations which are away from the large complex structure point. This is just for those who worry about mirror symmetry. Okay, let me speed up a bit. So type 4, decompactification to 5 dimensions. Now type 6 is very similar. In this case, let me show again, type 3. This was a T2 fibered over an S1, and there are 2 S1s, so we have now 2 such 3 cycles. So we have 2 leading vanishing 3 cycles. They are also topology of a 3 torus, namely S2 over S1. So we get 2 towers of BPS states by the same argument. Again, wrapping number is independent. BPS index is independent of wrapping number. So they both behave as Kaluza-Klein towers. So we decompactify to 6 dimensions. And in fact, we can argue that the 2 BPS numbers are the same and are again given by minus chi, but minus the Euler characteristic of the threefold, because we can always distinguish one of the 2 towers and degenerate the singularity such that it becomes that the 3 cycle becomes small a little bit faster. This means that we tune the type 3 singularity to become a type 4 singularity. So these 2 3 cycles, one of them we can make sure becomes small faster than the other. And then this one would be a decompactification to 5 dimensions. So its BPS number is given by minus the Euler characteristic. I can do that for both of them. So they both have to be of this type. And this, to my knowledge, is a new result. At least I didn't find it in the math literature. Maybe it's there, but this is a physics type of derivation. Okay, so that also works with the emergent string conjecture. We have now a KK tower from 4 to 6 dimensions in this case. And the remaining case is the most complicated one. This is a type 2 limit. And we claim that this becomes a weak coupling string limit, an emergent string limit. And to do this, one has to work a bit harder because we now have 2 types of states that become light at the same rate. First, let me start with number 2. We also have the 3 branes, again, wrapping these 3 cycles, but the topology of the 3 cycles is more complicated. And then, in addition, we also have a string becoming light. And to see the string, we have to carefully identify the supergravity BPS strings or EFT strings. I will come to this in a second, and have to use the topology of that intersecting surface. And putting everything together then will give you that this BPS string that becomes tensionless is a critical string that's important. And second, that these extra D3 brane modes should be interpreted as winding and KK modes associated with that string. So I'm running out of time. I'll be rather brief now for the next 4 minutes or so, just to give you the idea. So the point is that these type 2 degenerations are in fact the most complicated ones. A special class is known as Theorem degenerations, and I'll first work for these and then generalize. So we have, in these Theorem, we have 2 components, 2 threefolds, which intersect over a surface, and in Theorem case, this is a K3 surface. So let's assume this for the argument. So the second cohomology class of this surface splits into what's known as the polarization and the transcendental lattice, respectively. The polarization 2 forms are those that are pulled back from 2 forms of the ambient space. And the transcendental ones is the rest. So it's those 2 forms which do not come from the ambient space. Why I'm telling you this, the point is that these types of 2 forms in the transcendental lattice turn out to be precisely the 2 forms over which I can fiber my S1 that shrinks in order to get a shrinking 3 cycle. That is the result of the geometric limiting mixed hot structure, and this was also discussed in these papers, in particular in this one here. So geometrically, the subindex B of the degeneration is nothing other than the dimension of this transcendental lattice of this K3, which arises at the intersection. More precisely, we have a lattice of signature 2, B. That's the first input. That comes from geometry. And the second input, that's very important, comes from supergravity. And this draws upon an important circle of ideas that was discussed in this paper by Fernando and collaborators. Namely, forget about geometry, only look at the supergravity. We have 4D n = 2 supergravity. 4D n equal 2 supergravity has chiral multiplets, so there's the modulus, say the Kähler modulus, but this is always paired with an axion. There can be objects charged magnetically under the axion. These are strings. Put differently, objects that couple to the two-form dual to the axion. These are BPS solutions of the supergravity. They have a priori nothing to do with the strings of string theory. They are simply solutions of the supergravity that are charged magnetically under the axion. Since these are strings in 4 dimensions in the 4D n equal 2 theory, they have a strong back reaction, like the cosmic strings of Wachter and friends. So in the vicinity of their core, the moduli have a change from the original asymptotic value far away, or at a certain point. And it turns out that the moduli precisely take values that correspond to infinite distance limits. All this was analyzed in this paper. And one can now look at small closed loops of these strings and compute the tension. And it turns out that the tension of these small loops of strings goes to 0 precisely like 1 over s in the limit s to infinity for these type 2 limits. So the idea would now be that these axionic strings in the 4D n equal 2 supergravity should be weak coupling strings of some critical type, so should be critical strings. And this was not known and was shown in this paper. So we analyze in detail now the worldsheet theory of these strings. It's a 0,2 worldsheet theory. We count the zero modes. The zero modes come from the geometric zero modes of this degeneration, but also localized zero modes from the type 2b background in the type 2b theory, and counting them carefully and taking into account the structure of these two forms that I just stated on the intersection, one can show that indeed these zero modes precisely reproduce the worldsheet theory of a critical heterotic string. So one finds a theory with CLCR equal 2412, and the interactions of these are compatible with this being a heterotic string on this target space T2 times K3, where the K3 in general is T2 fibered over some base, and the base goes to infinity only in the limit, but this is an artifact of the limit. So the key message is that one can compute the worldsheet theory of the supergravity strings and map it to the worldsheet theory of a critical heterotic string. And this was only possible because this surface here is a K3 surface. Had it been like a P2 or something like this, we would not get a critical string, but a non-critical string. Okay, I spare you the details. If you want, we can discuss this later, so we can make a precise dictionary and map between the various types of fields and their interpretation from a heterotic point of view. Good. So we have this emergent string, a weakly coupled string that becomes tensionless, and that is the heterotic string. Now, if we have the heterotic string in becoming tensionless, this means that in the dual heterotic frame, the string coupling must become small. But in that case, there must also be a KK, a winding tower, at the same string scale that also becomes light with respect to the Planck scale. That's just how it works in string compactifications. And the claim is that these extra winding towers of states are precisely the D3 branes that wrap these vanishing 3 cycles on the type 2b side. So more precisely, the 3 cycles that we have in this type 2 limit have the topology of an S1 over certain 2 cycles on the K3. Precisely those 2 cycles, which are of non-negative self-intersection, turn out to give rise to a tower. One can argue for that easily. One can count them, and one can see that this indeed coincides with the lattice of winding and KK towers of the dual heterotic string that one would expect. So the supergravity string gives the emergent string, while the D3 branes in this context are not KK modes just taking us from 4D to 5D or 4D to 6D as before, but they are simply the accompanying lattice of winding and KK modes of this dual heterotic string. And in fact, one can go further using this. Now again, by physics, one can make a statement about the counting as we did before. And the statement would be that this counting, that the counting of the corresponding 3 cycles should reproduce the counting of these winding and KK states on the heterotic side, and that this counting function should be some meromorphic form. And finally, let me also point out one thing. I described this for the example of a Theorin degeneration. Recall, let me go back so that you know what comment I meant. I said here, assume that they intersect over a K3 surface. Now I saw this is crucial in order to get the perturbative heterotic string. So if there were a situation, a type 2 limit, where the intersection is not about a K3 but some other surface, we would not get a perturbative heterotic string, but we would get something else. This is in contradiction with the emergent string conjecture, because the conjecture is that at infinite distance, you always find either decompactification or a string limit. And this case, for certain reasons that one can already see in the supergravity, must be a string limit. It cannot be a pure decompactification. So this means that these, the only intersection surfaces that can occur should be K3 surfaces. There's one more option. These would be T4 surfaces, in which case the dual string is not a heterotic string, but a type 2 string. And this is therefore the conjecture. Again, a conjecture now from the physics to the geometry that in such type 2 limits, the intersecting surface must always be K3 or T4 surface. So it would be very interesting to verify this independently in the mathematics. And I should say once more that, yes, and you already anticipated the question, what is now the dual of that? The dual of this in the type 2A case, when a dual exists, would be that of a K3 or T4 vibration, where the base becomes large on the type 2A side. And this case has been studied in great detail already in the original paper with Sinju and Wolfgang, and also in subsequent ones. Okay, so this finishes the part 1 on type 2B. And now in the remaining few minutes, let me move on to the second part. This will be much shorter, namely something completely different. So if you decoupled, you can come back for 10 more minutes, something which I hope you find amusing at least, testing the perturbative heterotic string. And the claim is axion experiments are super relevant because they may rule out the perturbative heterotic string. I was shocked when I heard about this from Mario Rake and their paper here, and we close a loophole in this argument that I'm going to report about. So very briefly, we all know the statement that string theory naturally gives rise to axions. And this statement was first made in the heterotic context. In fact, it's particularly nice to talk about this here in Korea because Choi and Kim were the pioneers of this field 40 years ago, precisely 40 years ago. They pointed out in particular that in the heterotic string, there are always two, in fact, three types of axions. There's the model independent axion by integrating the famous 6 form, which is the dual to the 2 form over the Calabi-Yau. There are the model dependent axions, 2 form over curve. This gives me a number of axions, H11 many. And in fact, in presence of NS5 branes, we also have axions from the self-dual tensor on the NS5 branes, if they are there. And the point is that one can compute the couplings of these axions to the gauge sector. They are of the type axion F wedge F, and this comes from dimension reducing the famous Green-Schwarz terms. There are couplings B2 wedge X8, whereas X8 is this anomaly polynomial, and dimensionally reducing this and also similar counter terms in the presence of 5 branes gives you precisely the couplings axion F wedge F. This was a famous, beautiful result that goes back 40 years ago. And in fact, the couplings look like this, and this is now the key observation. Even though there are many, many axions, there are only 2 combinations that couple to the gauge groups in the first E8 and second E8 respectively, at least in models without line bundles. I'll come to this. Namely, we have the trace of the first E8 and the trace of the second E8, and what couples to them is a linear combination θ1 and θ2 of these axions that I described with coefficients that can be computed. They are irrelevant for us. Why is this interesting? And this is now the observation of Rake and collaborators. Suppose now you have your standard model from 1E8. This is how it was for a long time thought the world would be, that this is the standard model is incorporated in 1E8 factor of the heterotic string. So every axion that couples to U1 electromagnetic, which comes from this first E8, also couples to SU3, because everything comes from E8, 1, and there's only one axion coupling, one linear combination coupling to this. So there is only one type of axion, so to speak, that couples to U1 electromagnetic directly, and that is the QCD axion. The QCD axion has a certain value for the coupling to mass ratio. If I now want to think, is there another axion that couples to electromagnetism different from this, then the only type of coupling can come by mixing kinetically or via masses with this original QCD axion. And their analysis shows that by this mixing, you will always get couplings such that the coupling to mass ratio for this new type of axion that couples only via mixings to U1 EM is always smaller than or equal to that charge to mass ratio, coupling to mass ratio of the QCD axion. This was pointed out in these papers. And in fact, it's not a property of the heterotic string, it's really a property of GUTS. And heterotic string is an example of that. So this is really a GUT structure. And they wrote this really remarkable paper showing or arguing, therefore, that if you find an ALP, an axion-like particle, coupling to electromagnetism, whose coupling to mass ratio, this is what you see here, this is the coupling, this is the mass. If the coupling to mass ratio lies here, this is larger than that of the QCD axion, which is this black line within a certain range, then this is inconsistent with the GUT. So, and this is fantastic news because there's a lot of experimental activity going on, MadMax, Baby Yaxo, ALPS2, many experiments trying to explore this region. So if they find an axion, GUTs are ruled out. I found this absolutely shocking. And since GUTs ruled out, also the heterotic string is ruled out to the extent that it gives rise to a GUT structure. However, the last statement has a loophole. And the loophole is that you can also have the perturbative heterotic string without such a GUT structure. Namely, you could think that you can embed hypercharge and hence electromagnetism not only into one E8 but into both E8s diagonally. More precisely, what you could do is you can have a gauge background that breaks E8 to something like this, something non-abelian plus a bunch of U1s from the first E8, from the second E8, and then you take a linear combination of these U1s such that this corresponds to hypercharge. Now, electromagnetism comes from both E8s, and the previous argument does not apply anymore because it really used the GUT structure. And indeed, it turns out that such examples exist. They are well and healthy. One can find 3-generation examples without any chiral exotics on simply connected Calabi-Yau threefolds, and make sure that one has such a non-GUT structure, even though one works in the perturbative heterotic string. So this would be a potential loophole. Before we discuss the loophole, one more word. These models are not perfect because one has to pay a price. The price for putting electromagnetism into both E8s is that the GUT relation is screwed up. Namely, the usual relation in GUTs would be that 1 over the hypercharge coupling alpha is 5/3 over alpha GUT at the GUT scale. And this relation comes out naturally in any GUT. Here it doesn't because the second U1 comes from a different gauge group. And in fact, there are two types of corrections. The first comes directly from the embedding. Ignore the details. This is a model-dependent topological factor from the embedding. And then there's a string theoretic correction that incorporates threshold corrections from strings running in loops. So for this to be a good model, we would need the sum of this embedding factor plus the string loop correction plus any corrections from intermediate mass states to sum up to 0. Only then is it a good model. So before we test a model at an axion experiment, you first make sure that the GUT coupling comes out right? So this would be a necessary condition. Okay, and now comes the point. So since electromagnetism comes from both E8s, it turns out that now there are two possible types of ALPs that can couple to the U1 without coupling to QCD. Namely, the second axion that couples to the second E8 will have a coupling to the U1. And because of the loop corrections, it turns out that there's always one linear combination of model-dependent axions that also couples to this U1. So these two could evade the bound and hence would destroy the statement that finding a light axion would rule out the heterotic string. And this is where our paper starts. The key observation, however, is that these two axions nonetheless receive a mass, which is somewhat universal. It's due to Euclidean NS5 brane instantons from that coupled to the second E8. this is an effect that is suppressed by e to the -1 over alpha of the second E8. And since at tree level, these couplings are the same as the couplings of the original gut model, one finds a structure that, that still allows us to make predictions. Namely, one can argue for this form of the potential at tree level first, something that is suppressed by e to the -1 over alpha gut with some extra factors. And this potential therefore gives a mass to these axions. And doing this, and I'm now going over all the details, one finds this, and this is my last content slide. One finds that in all models that are perturbatively under control, one can still make a prediction. The coupling to mass ratio of all ALPs in such heterotic models must always lie to the left of this brown curve here. To the right, must lie to the right of this brown curve. So in other words, finding an axion over here would rule out also this type of heterotic models. There's some model dependence now. The model dependence comes from the thresholds that one has to consider carefully. They depend on the SUSY scale, but the worst case would be where there is no supersymmetry at all up to the string scale, and then one still finds a prediction that in the most conservative way looks like this. So if Mad Max finds an axion here, the perturbative heterotic string is ruled out. And more importantly, there is already a candidate for such an axion. Namely, there's something called cosmic birefringence. That's the fact that the cosmic that the polarization in the CMB changes. This might be due to a very light cosmological axion in this ballpark. This would lie over here. So if this effect stays and is really due to an axion, this has ruled out the guts and also the perturbative heterotic string in that sense. Okay, so to summarize, in the first part of the talk, I tested the emergent string conjecture by these stable degenerations, and we confirmed the expectation from the emergent string conjecture by combining algebraic and geometric insights into the degenerating geometry. And in the second part, I want to end with a very optimistic note, namely, even though the string scale is very high and probing it directly is difficult, there can still be interesting experiments at low energies, like in this case, axion experiments that might tell us something very interesting. So again, UV-IR mixing also is realized in this context, maybe by accident. And finally, it's my privilege to say something that we all share, I'm sure, namely a big thank you for a wonderful meeting here in Seoul. We all enjoyed the meeting very much. You were fantastic and wonderful hosts. So thank you very much to the organizers for bringing us here. Thank you.
Thank you very much for the nice talk. Any questions?
Case. Can you imagine, the axion not coupling to visible sector at all? Something that, astrophysics people recently discussed a lot, the so-called fuzzy dark matter,
right,
which is at 10 to the minus 22 electron volt around, somewhere around there. And that seems to have a real possibility of sort of indirect detection by looking at astronomy. And I was wondering whether this coupling, your bound requires coupling to photons.
That's right. So
is that obligatory in heterotic theory, you think? Or
yeah, everything on this side would be fine. So as long as the coupling to photons is very, very small, we are good.
But I was more of asking whether coupling to photon would be sort of obligatory if you start with perturbative heterotic theory.
No, there are,
there are other possibilities.
Exactly. So in particular, some of the 5-brane axions will not be coupling.
Oh, that's right. 5-brane,
yes. There are only two combinations that couple to. So these scenarios are still very well possible. Yes, I see. The ones that you talk about, where you have no coupling at all.
Thank you.
And there was also a paper I should have put in this paper. I apologize, by Westphal, Putti, and Liedem. My colleagues, in fact, from Hamburg. I'm sorry that I forgot, because And they focus on this scenario, not so much on the coupling to the U1, but more the cosmological. And for these then, for example, worldsheet instanton effects, which are discussed in great detail in their paper, play a role. Yes.
I'm not sure I understand the, well, thanks for the nice talk. I'm not sure I understand the sense in which you're ruling out axions and gut models. So are these stringy axions, or if suppose it was just a Peche-Quinn axion or just some low energy effective field theory axion, you're saying that would also be ruled out? And are you assuming there's no like intermediate strongly coupled stuff coupling to the sector in between the gut scale and the kind of, 125 GeV
Yes,
scale?
I think that's the claim. More precisely, that's the claim in, not by us, but already in the first paper here.
Yeah, I don't understand that claim. So
that is the claim. Everything that has a coupling to the U1 must also have a coupling to the SU3 and vice versa, unless you have a mixing to SU3 by kinetic or mass mixing, but then the inequality is satisfied. This inequality is satisfied. That's a consequence of the gut structure.
yeah, but you can violate that a little bit and still have gauge coupling unification. So you don't have to have exact like gauge coupling. You don't have to have everything in exact gut multiplets to still have gauge coupling unification.
Yes, then you're not in a gut anymore. Well, it depends on what you mean. It depends on what you mean by a gut.
Okay, okay. Let's take an F theory model, put a D3 brain next to it. It's sensitive to the electroweak symmetry breaking. So everything is not coming in exact gut multiplets. It runs the coupling slightly differently. So I haven't checked it in this case, like what happens, but.
So the definition here is that that SU3 to 1 come from one simple gauge group. That's
happening in the F theory gut model. I just add an extra D3 brain probing the F theory gut.
Yes.
It runs the couplings differently though. So 3, 2, 1 get run slightly differently. So I haven't checked in that case what happens, but I'm not sure that relation has to hold.
I think that is their prediction that this relation will hold.
I don't think so.
Please check their paper. And
I will. I'm suspicious. Anyway.
Any other questions? Okay, if not, let's thank Timo again.
Thank you.